And coming up right now, The Space Show.
This is your community radio station, 88.3 Southern FM.
Welcome to The Space Show, presented by members of the Space Association of Australia, and hosted tonight by me, Richard Van der Sprinkle. Andrew Rennie is on a short hiatus, but will be back with us in a couple of weeks. Now, we are potentially just hours away from the launch of the Artemis II mission, which will send the Orion capsule and its 4-person crew on a journey around the Moon and back. So in keeping with that lunar theme, on the show tonight we'll be exploring lunar astronomy, that is astronomy conducted directly from the Moon's surface, where the lack of atmosphere or radio interference offers some remarkable advantages. We'll also be taking a look at lunar geology later on, and how it supports the Moon landings. But first, let's take a look at the latest in space news. We begin with an update on Artemis II. At this stage, NASA's official countdown is still targeting a launch time of 6:24 p.m. from Launch Complex 39B at the Kennedy Space Center in Florida. For those of us here in Victoria, that translates to 9:24 a.m. AEST tomorrow morning, so not long to wait at all. Wishing the crew the very best for a safe and successful mission. In a related development, Australia will be playing a direct role in supporting Artemis II. NASA will be flying an optical communications system aboard the Orion spacecraft, and the Australian National University's Quantum Optical Ground Station at Mount Stromlo Observatory in Canberra will be used to track, transmit and receive communications. This will open up the potential for optical ground stations to support future lunar missions. The announcement was made by ANU Professor Francis Bennett alongside CSIRO's Kevin Ferguson, Director of the Canberra Deep Space Communications Complex, and Australian astronaut Catherine Bennell-Pegg. Finally, NASA has selected Intuitive Machines to deliver Australia's first lunar rover, named Rover, to the south pole of the Moon in 2030 as part of the Commercial Lunar Payload Services, or CLPS, initiative. And for those keeping track, yes, that's Rover, ROO-VER. It will be one of 7 payloads delivered on the mission. And for those worried about the tipping issues Intuitive Machines have had in their last couple of missions, well, they'll have a couple more opportunities before the 2030 Rover delivery, so they will be well practiced by then. Now, staying with our lunar theme, let's head to our feature on lunar astronomy. Here is Martin Elvis, Senior Astrophysicist at the Center for Astrophysics at Harvard and Smithsonian. Speaking at the 2025 International Astronautical Congress in Sydney, he outlines why the far side of the Moon could be the perfect location for conducting radio astronomy.
Okay, I'm going to talk about astronomy from the Moon and the cornucopia of science that it could deliver, but also some of the challenges it faces in being able to continue that activity sustainably. So if you haven't heard of doing astronomy from the Moon, that's not surprising, because even a few years ago, almost all astronomers, including me, thought this was a silly idea that had no value at all. Not all, but there were a small clique who persisted in pointing out the usefulness. But as plans for a human base near the South Pole have emerged and become more imminent, astronomers started to realize that if you have astronauts and you have tons of equipment being landed on the Moon, all within a decade, that becomes an interesting parameter space to start thinking about, can we put some telescopes on the Moon? And it becomes a real opportunity. So around the end of the pandemic in early 2023, I helped convene a meeting at the Royal Society on astronomy from the Moon, and we gathered about 50 astronomers from in London from all over the world for 2 days of talks about these new concepts. And they brought up ones I certainly had never heard of, spanning most of the electromagnetic spectrum, from the ultraviolet to the radio, the very low frequency radio, and even in gravitational waves. And this meeting seems to have generated some momentum and led to several professional meetings afterwards. And we're on a roll, and I hope you'll see why. So why the excitement? Because this science that we can do spans an enormous range from the dark ages of the universe, when before there were any stars or galaxies, right up to finding nearby alien civilizations, should they exist, or at least life on other exo-Earths. So I'm going to limit myself to 5 examples. As I wrote the talk, I realized there was a theme here, and that is that our computer simulations have become so good that they look so convincing in the videos that the people produce from them, that we feel convinced that they must be right. But in fact, in many cases, we have no data to test those models. And astronomy from the moon may enable some of those tests to take place. So here's the first example out of 5. It's a plot of the first billion years of the history of the universe. That's until the universe was 10%, a bit less than that, of its present age. So it's the early baby pictures almost of the universe, stemming from the Big Bang on the left to the first formation of stars on the right. The first stars seem to have formed around redshift 10, 12, maybe a little higher, after a few hundred million years of the universe becoming in existence. And that era is being wonderfully observed and opened up to the investigation by the James Webb Space Telescope. And we needed the James Webb Space Telescope because this is all happening at a redshift of 10, which means the universe was 10 times smaller then and has since expanded by that factor. And that stretches out the light from the normal optical ultraviolet bands where we study stars locally into the infrared. And that's what James Webb was designed to do, and does it beautifully. But you'll see that there's this gap called the Dark Ages, when there were no stars. And that seems like maybe there was a quite boring era, but in fact, no. In that era, we went from parts per million of fluctuations in density over the whole universe to places where the density becomes so high and the temperature becomes so high that hydrogen burns and fuses into helium. In other words, the middle and insides of a star. How does that enormous range of density and temperature come into existence? We have simulations of what must be happening. They look convincing, but are they right? We don't have any data from the Dark Ages to test that. There is just one possibility. There's the one thing there was a lot of in the early universe is hydrogen, and hydrogen has one emission line, one transition in its atom, which can absorb or emit at a wavelength of 21 centimeters or 1.4 gigahertz in frequency space. And that is a tool we use locally in the universe, very much so to map out the structure of the Milky Way, or to see streamers of hydrogen gas pouring from one galaxy to another. But that's great locally at 21 centimeters, 1.4 gigahertz, but unfortunately, we're now talking redshifts of nearly 100, and so that radiation emitted at that 1.4 gigahertz has been stretched out to be 100 times longer wavelengths, and that is a problem for detecting it. What about life? And example 2, what about life and detecting aliens? Well, we are protected by the Earth's magnetic field from the radiation in space, from the solar wind and so on. So if we could work out which exo-Earths, meaning terrestrial-sized planets in the habitable zone where water can be liquid, which if we also we're able to filter on those which have magnetic fields, that would focus our attention onto more promising Earth-like planets. So what we could do with the low-frequency radio emission is measure their aurorae, like the aurora australis here, and that would tell us that there was a magnetic field protecting the surface of that planet. If we want to be more dramatic, we could ask if any exo-Earths have technosignatures. Are they emitting radio waves as we have been for about a century now? And can we set limits on how much they do that, even if we don't detect them? Or maybe we would detect one. Apparently, this can be done out to perhaps 100 light years from here if you had the right telescope with the right sensitivity. But the problem is, and old people in the audience, or senior people in the audience, will recognize this as a tuner for a radio. And I got it because it mentions the actual frequencies we're talking about. We're talking about tens of megahertz here, and that's a problem because that's where we are emitting lots of radio emission. So the noise on Earth is huge, not to mention the atmosphere is a problem, and that makes the dark ages and alien life undetectable from Earth. Third example is listening to the hearts of giant stars as they explode, supernovae. After 50 years of trying, computer modeling of supernova explosions failed to make them explode. They would be failed explosions. They'd try to expand but collapse back. But we know that they do expand. This is a Chandra X-ray Observatory image of the Cassiopeia supernova remnant, and each one of those different colors is a different element that was created in the supernova explosion, being forced out into the interstellar medium, where eventually it becomes condensed into stars and planets and, in fact, us. This is where the star stuff comes from. We are star stuff. Chandra has measured this Cassiopeia A supernova remnant over 20 years now, and it's been able to see that those little filaments have been expanding. And you can tell how fast the thing is expanding, and of course you can then extrapolate back, and it's about 300 years old. So now, most recently in the last couple of years, it's been thought that we've solved the problem of making supernova explode. And the key was in that the explosions are very much due to three-dimensional effects that only exist in 3 dimensions. So you have to have a very full-up 3-dimensional simulation. And they are very non-spherical. So here is a high-resolution image of this from the model. This is a full 500 milliseconds after the first explosion. And yet already you can see it's extremely non-spherical. And what you can't tell from this picture is that there are outflows, of course, from the explosion, but there are also very fast inflows, which keeps the energy density high and keeps the explosion happening. And so this is the claim that we now understand how supernovae explode. Or so we think. But this is just theory. There was no test of this model. Because how do we test what happens in the first half second of explosion inside a star where we can't see what's going on? And they're very complex models, so could some of the nuclear physics be wrong? Could some of the neutrino physics be wrong? There's a lot of possibilities for making errors in these things. We need to test them. So how do we test them? One answer is to use this asymmetry, because when you have large masses moving very fast in a very non-spherical way, that's exactly the conditions you need to generate gravitational waves. And so that's going to be an interest, and that has a signature which some calculations say comes at a particular frequency that can only be detected, guess where, from the moon.
Martin Elvis continues, outlining why the far side of the moon provides such a unique environment for radio astronomy.
If we look at the stars, they look like twinkling points of light, and we tend not to think of them as real objects in their own right. And even if we did, you might think, well, we don't really need to image the stars because they're kind of boring. This is a picture of the sun, and there's not a lot of information in that picture. Why should we go to a lot of trouble to image stars if that's what they look like? The answer is that's not really what all stars look like. If we can make hundreds times sharper images than Hubble or Webb, but only for the brightest stars. With using an interferometer. There are 2 in existence. One is on Mount Wilson in California, and it made these images of stars showing lots of very strong star spots, that not everything is spherical, but squeezed. In fact, they can be quite irregular in shape. The problem is, why don't we just keep using this? Well, the problem is the atmosphere wobbles so much that the integration time you can have, the exposure time, is just a millisecond, after which the turbulence in the atmosphere changes the phases of the photon wavefront coming in and makes it impossible to see fringes, which is how interferometers work. So, and if we could get better signal to noise and cover all the scales available, then Betelgeuse is predicted in a complex computer simulation to look something like this. It's a three-dimensional boiling pot of convecting water, well, of course, it's plasma in this case. And that would be, and it would be a movie because this stuff is moving quite fast, and we could watch how that turbulence happens. If you can image if you can image stars, can you actually image exoplanets, exo-Earths in particular? When I say image, I mean not just detect a point of light next to a host star, but actually make an image that can do enough to see whether you can see oceans, continents, a mixture of those, cloud cover, and just possibly vegetation. That would be a wonderful thing to be able to do, but of course this is visionary. It's beyond what we can do at the moment, and would be, even on the moon, would be a distant prospect. But I'll show you what might happen. So I hope you find those 5 examples reasonably compelling to say, we wish we could do that science, how are we going to do it?
Next, Martin explores how lunar-based radio astronomy could actually be implemented and the advantages it offers over Earth-based systems.
So for the low-frequency radio that we would like to use to measure the dark ages and look for life elsewhere, the answer is to move your telescope to the far side of the moon. What's great about the far side of the moon is that it's extremely radio quiet. Here's a data analysis challenge for you. The actual degree by which the background noise from the Earth is cut down, 2,000 kilometers of rock, that's pretty useful. The actual factor by which it's reduced is predicted to be absurdly low. It's 100 million times fainter than the front side. I don't think there's any other case in astronomy where you can look for a factor of 10 to the 8 improvement in your background or any other criterion you choose. So this is pretty darned remarkable. Is it true? Well, we can only tell if we go there and check. So already as a result of this, and before our meeting in London, this was a active field. Several people had ideas of how you might do this. Here's half a dozen of them, starting with a clever Chinese proposal to have a chain of satellites in orbit around the moon, separated by probably 100 kilometers altogether. And when they go around the far side, the far side, they would be able to start imaging the background and see if they can find this signal from the dark ages. And then there are various possibilities on the ground on the far side, and I can show you there's a European one, two NASA ones, another Chinese proposal, and the ultimate telescope for this purpose would need to be 200 kilometers in diameter. It's just an array of dipoles, but it's still big. And at that point, you resolve all of the 1 million gas clouds that eventually combine to form a single galaxy. And this overcomes some of the problems with using galaxies to determine the structure of the universe, because the universe just doesn't have enough galaxies. So the good news is there's going to be, even next year, there will be at least one first measurement, so long as the landing goes well, but it's Firefly, so it should do, on the far side, to actually check out whether the noise level is that much lower than we thought, than as predicted. Excuse me. The gravitational waves are an interesting case. Prediction by some calculations is that the characteristic signal of supernovae exploding will take place in a region of parameter space, a frequency of gravitational waves that we have not yet probed. In a few years, the LISA mission from ESA will probe very long wavelengths and be able to see black holes merging in distant galaxies. Already we have LIGO, Virgo, and CAGRA taking measurements on the ground. They work at higher frequencies and a much shorter wavelength, much shorter measurement arms. But that leaves a gap which is about 2 decks wide, a factor of 100 wide. And guess what? That's exactly where some calculations say the characteristic signal of supernovae lies. But you can't do that. You can't examine that frequency range on Earth because of noise, both seismic activity and human activity, trucks driving by, basically. And of course, the moon is far quieter in seismic activity and has no, currently, human activity. So that's very promising. So how are you going to do it anyway? There's 2 approaches. The first one is to put a kind of super LIGO on the moon, this time in a triangle and 40-kilometer sides instead of 4. That's a problem because you can't put it anywhere on the moon because the horizon is just a few kilometers away. So the trick is to put it on the edge of a crater, which of that size, so you can have a clean line of sight across. You'd really like to have a cold, cryogenic environment because the mirrors that are hanging there and reflecting the laser beams have thermal noise in them, and if you can reduce that, you can increase the sensitivity of your detector, and you can do that by not going down a little bit into the permanently shadowed regions of your chosen crater. The alternative is to measure the distortion of the whole moon using seismometers. The moon gets squished and pushed by the gravitational wave, the quadrupole nature of the gravitational wave. True motion is a small fraction of the width of a proton. And yet this is apparently, and I'm no expert, apparently detectable. And the idea is to have an array of these around as much of the moon as you can cover in order to triangulate the position from which the gravitational waves has arrived, because that will allow you to look in other wavelengths for electromagnetic counterparts, whatever wavelength. Again, permanently shadowed regions are favored because we like it to be cold, and a lot of the power goes in cooling the first part of the cooling cycle. It's down to like 50 Kelvin. And one of these would be great for studying the inner structure of the moon. So maybe we can join forces with the lunar scientists, and this is far more sophisticated seismometer than they are currently planning to put on the moon. It would be good to land just one of these, not the whole array, just to see what the seismic background truly is at the levels of interest. If we want to image the stars like Betelgeuse, then you have to have a telescope that's 100 times the diameter of Hubble or Webb. And that means you're moving up to kilometer scales. And certainly you can't have a single reflecting mirror there. You have to use an interferometer. So here is one example of how that might work. You put telescopes out on the lunar surface. Each of the telescopes sends its light to a beam combiner, which measures fringes between each pair of mirrors, of telescopes. This particular one is taken from the Artemis-enabled stellar imager study, led out of Goddard Space Flight Center, which seems it's quite ambitious. They want at about 30 1-meter class telescopes. You need a lot to cover a lot of different baselines to get fill in the image properly. The key thing is, compared with doing this on Earth, where you have 1 millisecond, you can easily observe for 1,000 seconds, so 1,000,000 times longer, and that will give you at least 1,000 times better signal to noise. So it's really quite a dramatic breakthrough. You can also look at far fainter objects, stars that are much fainter than we can do on Earth. But why put it on the moon and not in orbit? Well, they studied that. You need precision flying, formation flying of 30 different spacecraft separated by tens or hundreds of meters, and to a tolerance, a fraction of a wavelength, which means at the longest 0.1 microns. If you can get into the ultraviolet, it means 0.01 microns, and that's extremely challenging. Instead, when you put these telescopes on the surface of the moon, they just stay put, and it simplifies the technology greatly, so long, of course, as you have that human base to be able to deploy these.
You're listening to The Space Show. We'll be back with more from Martin Elvis after this short break.
You're listening to 88.3 Southern FM, the sounds of the Bayside.
Welcome back. We're listening to Martin Elvis, Senior Astrophysicist at the Center for Astrophysics at Harvard and Smithsonian, speaking at the 2025 International Astronautical Congress in Sydney. Here he turns to the topic of exoplanet imaging.
And lastly, how would we build a big enough telescope to make an image of an exo-Earth? From the European Southern Observatory, their current big telescope is the Very Large Telescope. They're building, after the Very Large Telescope, they're building the Extremely Large Telescope, 39-meter diameter primary mirror, and getting up to proper. But that's actually a step down from what they first looked at building, which was an overwhelmingly large telescope with a 100-meter mirror. So they decided that although they'd love to build that on a big mountain site out in Chile, it could not be done because of wind shake, because of gravity sag, and because you're still trying to be diffraction limited at 10 times the diameter of James Webb Space Telescope, and that's a real problem when you're underneath an atmosphere, wobbling atmosphere. You have to make corrections with clever, fast-moving optics called adaptive optics. And the complexity of those is said to scale at least to the cube of the diameter of the mirror. So it all gets it rapidly runs away as a problem, a technical problem. But of course, as you all know, none of these are going to be problems in space because there's no wobbling atmosphere, there's no or reduced gravity, and there's no wind. So what you ask, why not put this telescope in a JWST-like Sun-Earth L2 orbit? Why not? Well, giant telescopes take a lot of construction, and you can't do a folding spacecraft, a folding mirror, the way JWST did, scaled up to fit a Starship. That's still much too small. So you've got bound to do complex assembly with many single-point failure modes out at L2, and that's very challenging. It's very complex. You can't use people to help you out there because the radiation is deadly. So it must be assembled by robots or tele-operated from the ground or from orbit. But that's got an annoying multi-second delay because it's 1 million kilometers away. So basically you've got a real problem. And once you get it built, you've got to point this telescope at different exo-Earths or other targets. And that means giant reaction wheels, because this has to end up being a massive device. And your accuracy to which you point and keep steady the pointing direction has to be 10 times better than James Webb Space Telescope. Extremely demanding. So surely expensive, and really that's quite discouraging. But at our London meeting in 2023, Jean-Pierre Maillard suggested a whole set of reasons why the lunar surface just might be the better place to do this. There was no sunshade needed because you use a permanently shadowed region. So slewing is easier, deployment is easier. There's no need to have onboard solar panels. In fact, if you're in a permanently shadowed region, that would be stupid. But you can put an array of solar panels on a nearby sunny ridge, which so means you can have much more power than you are otherwise limited to if you tie it to the spacecraft. So decoupling the systems. you can also eliminate a number of systems. There's no need to maintain the orbit with propellant, and because the moon is going to stay in its orbit regardless. And so the lifetime is not limited by that. It might be limited by other things, but there's no inherent limit because of that. You don't need reaction wheels because you're pushing against the surface of the moon, which is fine. So slewing is much easier. And you're on the moon's surface, which is a very stable platform, so it's reducing the problem of jitter, but not eliminating. I'm sure there will be mechanical problems, but issues, but certainly making it a lot easier. And servicing, which is bound to be needed and has been demonstrated to be a very powerful effect with the Hubble Space Telescope, you can't do that very easily at L2. It has to be all robotic and pre-thought out. If you have humans, astronauts at your lunar base with supplies coming in by the ton, then it's going to be much easier to service and repair than at L2. Altogether, Jean-Pierre suggests that these together might mean that we can do a cheaper mission and perhaps may even make the whole mission feasible. Not by any chance immediately. This is clearly a distant prospect even now, even with bases on the moon, but it certainly shows great promise.
Martin now discusses some of the sustainability challenges associated with conducting astronomy from the moon.
So what are the sustainability challenges I mentioned in my title? There are several. I should have said challenges instead of threats. It sounds a bit too aggressive. For the low-frequency radio, it's unintended electromagnetic radiation, which comes not from the direct communication channels which happen at gigahertz frequencies, but from stray noise from the electronics, the electrical systems like power supplies and motors, winding harnesses, wiring harnesses. And that happens in the megahertz range, which is just where we want to observe the dark ages signal. So that's a problem. On the moon, any kind of gravitational wave, it depends deeply on having low seismic activity, and human activity could contribute to noise, so you want to make sure that your gravitational wave detector is a good distance from your base, where the landings and takeoffs and mining equipment might be operating. So we don't know yet how far away that ought to be. That has to be studied, but it's clearly a concern. And for optical, infrared, and ultraviolet interferometry, dust is the real problem, and dust can be kicked. If you're in a permanently shadowed region, you don't get the lofting by the UV radiation that causes dust to rise up about a meter, but instead you do have the possibility of launches and landings creating enormous amounts of regolith and sent off in all directions at a low angle, and that could cover, if that coats your mirrors, you're in real trouble. And mining is a more ongoing possibility than landings and launches, which you could just shut down for and cover up the mirror. But if there's mining going on, like water mining in a permanently shadowed region, then that could be a continuous source of dust that you have to worry about. And, well, none of those possibilities are regulated whatsoever at the moment. The types of problem, the threat you're looking at can be global or can be local. And the global one we know about is the timing PNT constellations around the moon, which are being planned. The ESA Moonlight one, I believe, is the most advanced. There's the Lockheed Martin Parsec system, but I heard at this meeting that maybe that has been mothballed. There is a Chinese system being planned, and I'm embarrassed to say I couldn't find the name of it while I was looking. And again, just at this meeting, I discovered there's a Japanese system being built. So there could be 4 systems going to be in orbit around the moon and producing that electronics noise that we call UEMR. The problem is that each satellite system has to have 4 satellites overhead at any one time to get all the information about your position and time. So with 4 systems, that would mean 16 satellites overhead. So each individual satellite has to be cut its noise, not by an amount that individually can get you below the threshold that would be a problem for radio astronomy, but 12 or 16 times lower than that. It's the aggregate that matters. The fix is probably pretty simple. We're talking about multimeter wavelengths for the radio emission from these electronics. And so a chicken wire, centimeter scale mesh would prevent most of that radiation getting out. A simple Faraday cage, Faraday screen. But of course, the engineers who are building these systems have never heard from the astronomers because we've only just woken up to this problem. And we need to be able to communicate with those people. So if any of you are involved and know people who are doing that, I would love to hear from you.
And in this final part, Martin looks at the rarity and the need to protect potential lunar telescope sites.
If you look locally, it's surprising how rapidly the options for where to put a telescope shrink down once you put in different criteria. So, for instance, we wanted a permanently shadowed region for a 40-kilometer on a side triangular gravitational wave detector. Well, there's only 3 craters at the South Pole which are permanently shadowed and 40 kilometers or so in diameter, and they are Shoemaker, Hayworth, and Faustini. But 2 of them are rich in water, from what we can tell, and so we want to avoid those because they're likely to be good mining targets, being very close to the South Pole, and we want to avoid all the vibration and dust from them. So it could be that there's actually just this one crater, Faustini crater, where we can put this telescope. It's a first analysis, we may find more, but it shows that they're rare. Previously a pretty unknown feature on the lunar surface, and yet it could be key to making these measurements. So the general lesson we found as we look at different cases is that these lunar sites of special scientific interest, SSSIs, we got to learn to say that easily, are typically rare and typically quite small. And that means we need to think about how we can protect them for use for astronomy, to preserve our science options, even if building this gravitational wave detector is decades away. How can we now ensure that there is a place to put it that is pristine and properly useful? On the other hand, the good news is they're typically rare and small, which means we're not asking to put half the moon or some huge area off limits to commercial or exploration activities. We're just asking for a few small spots on the moon. Now, rare, valuable real estate is known to be a great cause of disputes and conflicts, and the question of how we go about protecting these SSSIs is an urgent one. And in particular, who will adjudicate any dispute? How will we settle a dispute? That's a big unanswered question. What we're doing about it is working under the auspices of the International Astronomical Union. They were very quick to have found a working group on astronomy from the moon just a few months after our meeting in London. And I have been made a co-chair of that, along with Chris Johnson of Secure World Foundation. I don't know if he's here. And Richard Green of University of Arizona, who's the chair of this and spends a lot of time in Vienna as a result nowadays, which is where UN COPUOS meets, the Committee on the Peaceful Uses of Outer Space. The goal is simple, and that's protecting these SSSIs, but to do that, we have 4 priorities. We've got to identify and justify the choice of these SSSIs. We've got to help develop reasonable policy or legal frameworks for designating them, and we need to work with all the different bodies involved, particularly with the COPUOS. The ATLAC Action Team for Lunar Activities Consultation was also rather quickly put together. I may have missed the backstory here, but it seemed like we said, we need something, and it sort of happened. very quickly. So maybe UN Copuus does not deserve the reputation for slowness that it has often been said to have. And then we're working with other regulatory groups. And we'd love to work also with other international organizations that want to protect other sites on the moon, such as the Apollo landing sites, which need protection, clearly, or other lunar science sites, where perhaps the coldest of the cold traps in the permanently shadowed regions have the best record of solar system history in volatiles that would otherwise be evaporated, or if mined out, if you go water mining there. That would be a shame if all of those disappeared. So what I've been working on is identifying and prioritizing these SSSIs. We're working with the PI teams, and the point is to develop a quantitative chain of reasoning that goes from the most general statement, like we want to measure these dark ages of the universe, using a science traceability matrix approach, where we drill down in each of the criteria, through the instrumentation, through the background, and therefore through the sites, and end up with figures of merit for each one of these sites, which allow us to rank them in order of importance. At the same time, we've been involved in several actions, and I'd like to highlight the very recent, last May, I believe, formation of a United Nations Friends of Lunar Sites of Special Scientific Interest. Several delegations have signed on, so it's very promising. And we also we're working with the Lunar Policy Platform and with COSPAR to work on a guide to lunar science and ethics, helping to put together the way in which you would designate these sites. So that's all very detailed. Let's not, however, step back and remember the vision, which for me is that we will want to understand our universe from our nearest neighbor world, and at the same time avoid repeating the mistakes we've made in low Earth orbit and on the ground. And what we do matters, because we are the first generation setting up this system. And as Wilbur Zielinski said, even a few score initial colonizers, he was thinking of the 13 original colonies of what became the United States, can mean much more for the cultural geography of a place than the contributions of tens of thousands of immigrants a few generations later. So the cultural geography of the moon is something we will be setting in this generation. And let us hope that we set a good example that will persist for a century to come or more. Because if we get it right, we will understand the universe and our place within it, and we'll be the better for it. Thank you.
It's exciting stuff. That was Martin Elvis, Senior Astrophysicist at the Center for Astrophysics at Harvard and Smithsonian, speaking at the 2025 International Astronautical Congress in Sydney. We'll be back with more on the Space Show after these messages.
88.3 Southern FM.
In November of 2019, Walter Keffer of the Lunar and Planetary Institute gave a talk on lunar geology, based on analysis of lunar samples brought back to Earth by the Apollo astronauts. Following the lecture, he was asked about the moon hoax, and his response is well worth a listen.
Thank you for your talk, Walter. As a lunar scientist, what do you say to those people from a scientific perspective that we never went to the moon? Because I keep running into them at airports and other places.
So first, I will tell you one of the great things of course, we didn't go to the moon for science. I mean, that's the first thing that's very clear. We went to beat the Russians. But I will tell you that the best thing we got out of the Apollo program is not the knowledge about the moon, which is fabulous, but what we got out of it is a generation of scientists who were committed to studying science in general. This is a story I told in this room, standing at this podium on July 20th of 2019, where I said to people that it's in fact not true that everybody was watching the landing on the moon. Of course, there was no pictures of the landing on the moon when they're actually landing the lunar module, when Armstrong's landing. But they had the radio thing. And I said, it's not true that everybody was watching on television, because I said, I know for a certainty that there was a 9-year-old boy sitting at a campsite in Northeast Texas, listening on his dad's battery-powered transistor radio, and then later that night, pestering his parents to stay up and listen to the moonwalk, and keeping up all night long. I still own the radio. We have a generation of scientists who got turned on not just to geology or planetary science or astronomy, but to science in general, that were inspired by those landings. The people that flew them will tell you that the kick in the pants, you couldn't simulate, you couldn't fake any possible way. Now, okay, you might say that if you don't want to believe it, you'll say they're lying. But the fact is that these rocks are just different enough chemically that they're not like the Earth. The basalt, and let me just take two examples. I told you the anorthosite from the Highland crust. There are places like that on the Earth, but not a lot. It's all over the place on the moon. And then the basalts. First of all, they have very little evidence of water in them, whereas it's almost impossible to avoid having water in basalts on the Earth. Go to Hawaii, you make basalts at those volcanoes. How do you avoid getting them wet? You can't. The biggest place we make basalts on the Earth is on the bottom of the seafloor. How do you avoid getting them wet? But the lunar rocks, almost no evidence of water in them. And then one other chemistry piece about it, the biggest way we distinguish the different types of basalts from the moon, we classify them based on, first of all, based on the element titanium. And so we call them high titanium and low titanium. And I promise you that if you told a terrestrial petrologist that this is what the titanium content of a low titanium rock on the moon is, they would look at you and go, that's enormous amounts of titanium. It doesn't happen that way on the Earth. So there are differences. The two bodies have subtly different compositions. You can't fake the ages. We don't have rocks that are that old on the Earth. And yeah, the guy in the street is going to say, well, how do I know the data? But enough different people are studying these things in enough different labs that you can't not do these side checks. So we know because the rocks tell us they were on a different place other than the Earth. Is that enough of an answer? Okay.
Won't satisfy that.
Well, okay, I have to talk as a scientist. If you're a skeptic in this country, don't get me started on that. And there's also this thing called the greenhouse effect, and it's real. And again, there are people that don't want to believe it because they just don't want to believe authorities. But I have to live as a scientist and live with the data, what the data is telling me. And the data is telling me that these are things from a place that's not like the Earth. And in very, very clear ways, it's not the Earth. And we got them back somehow. And I watched them. And we talked about Jack Schmitt at Belle Crater. Is that something he could have practiced? Probably not. I mean, let's just be honest. I mean, it's just not something you could have done. It's people working in a different gravity field. The pictures, I think, tell you too that it's different than the Earth. And if you don't want to believe it, you don't want to believe it. I can't force you to. But the evidence is in the data they brought back. Well, yeah, and that's a good enough reason for me, Lisa. But I got to tell a Jack Schmitt story while we're there, and forgive me if I'm running the time over. But on the Japanese sent a spacecraft to Jack Schmitt, of course, was the lunar module pilot on Apollo 17, the last landing, the only non-pilot to land on the moon. Got his undergraduate degree at Caltech. PhD from Harvard, and he got a chance, and he's a really bright guy. He learned to fly jets and to fly helicopters in order to qualify to do this. And he lands there. And anyway, years later, the Japanese sent a spacecraft to the moon called Kaguya. And one of the experiments they included on there was a high definition television camera, which was massive. And we all looked at each other like, what the heck are these people thinking? Well, after they come back, they released a video disc of some of the pictures, and you can find small versions of these on YouTube now. But seeing them in full scale on an HD television is the right way to see them. And we were, at that point, we were still meeting, our Lunar Science Conference was still meeting at South Shore Harbor in Lake City. And in the lobby, we had set up a television where we were playing these. The Japanese kept a security guard there to keep anybody from stealing the disc. And I'm sitting there and I'm mesmerized by this. And I realized I've missed like 3 talks that I was intending to go see because I'm just watching thing after thing after thing. And then there's this guy standing next to me. And wasn't paying attention to who was there. And then he says, it's the only thing I've ever seen that looked like what I saw from the command module. And I looked over and it was Jack. Now I've known Jack for a while. It's not like I get to interact with him a lot, but I have had that privilege, and I've met a few of the other astronauts along the way. But yeah, I mean, so yes, if Jack said he did it, well, he did it. But you know, for the skeptics, you know, there's data, and you're getting data from literally thousands of scientists science is a self-correcting process. And people do sometimes get things wrong in science. Like I said, you know, what they thought they were going to find in Apollo 16 is not what they found. Science is a self-correcting process. And so eventually the truth is going to come out. And these measurements by group after group after group says these are not like Earth rocks. The processes are familiar. The details are different, and they're different in ways that reflect the differences between the Earth and the Moon. That's how we know we went to a place that's not on Earth. That's how we know we went to the Moon and brought rocks back. Good enough?
That was Walter Keffer of the Lunar and Planetary Institute. And to finish tonight's show, just a few hours ago, NASA astronaut Jessica Meir, hope I've said that right, captured an image from the cupola of the International Space Station. The image shows the Artemis program mission patch floating against the backdrop of Earth, the blue and white marble we all call home. To close, here is astronaut Tracy Caldwell Dyson describing what it's like to look down on Earth from the cupola.
The shuttle, with its forward windows, was the closest thing we had prior to that to a cupola. But even then, because of the orientation of the vehicles with respect to the trajectory and the way that the shuttle docks, your view is quite limited. But the cupola, not just being the bay window, not just having 7 windows into space, but the location of it, and then the orientation of the space station, where we are, for the most part, usually belly down, and the cupola is pointing right at the Earth. And the way that it's shaped, you see all Earth, but then you can see space in the area around the base of it. The vantage point is so perfect for looking at the Earth. I think that as hard as it is to provide windows in a pressurized vehicle in the vacuum space, I totally get that. I just think that because we are humans in space, it's essential for what we're doing. We're exploring, we're observing. It's vital. And I think it's changed our ability to even describe the experience. When you're looking out the windows of the cupola and you get to see the curvature of the Earth and the blue hue of the atmosphere, and depending on the angle of the sun, these pearlescent yellows and peaches that form when you're looking at a body of water, it's just amazing. In fact, it almost, I dare say, grieved me to think about how in the world am I going to describe this? There's no words. There's no picture I could take to do it justice. There's no watercolors that I could put on paper to come close to the vividness, the ever-changing picture that I see staring at this planet. Everything from the colors to what changes the atmosphere goes through, depending on where the sun angle is and whether the moon's in the view or not, to just how fast we're going over the surface of it and the way shadows are changing. You could see the same landmass over a period of 2 weeks and it looks completely different because of that. To then looking at the stars and the blackness, a black that nothing here on Earth ever can replicate. And looking at that magnificent engineering marvel called the space station, the whole thing is just, it's a candy store.
That's all from the Space Show for tonight. Thanks for joining us as we explored the moon and the future of lunar missions. We look forward to having you with us again next week.